very much. And welcome to Ian Duncan of Tapeo, who's going to start our session today on green heating solutions. Thank you, Ian.
Great, thanks, Lindy, and yeah, thanks everyone for joining today. It's really good. It's encouraging to see so many people. If I just share my screen briefly, and yeah, Lindy, if that doesn't come through, then please shout. I assume that's come through okay. So yeah, I thought I would start, and I'll be as brief as I can with a quick overview of why low carbon heating matters. Touch on the technologies on one side of a fairly fractious debate, and then touch very briefly on the other side of the kind of roster of technologies that are available. I'll then swiftly move on to Tapeo, what we do, what our product is, before handing over to the next speaker. But I thought it'd be useful to put this whole thing in a bit of context. So decarbonising heat is essential for the UK to get to net zero. It's essential for more than the UK as well. Obviously, there are hundreds of millions, billions of people around the world who rely on fossil fuel heating to keep themselves warm and healthy. In the UK in particular, though, you know, we've got 30 years less now to get to net zero. That's enshrined in law, and there have been endless papers written on the kind of pathways required to get there. Every single one obviously includes heating. We're a country of 85% gas central heating in the UK, over 90% fossil fuel driven, including oil, LPG, and other forms of heat. But while it's a huge problem, you can see from that sort of exploded pie chart in the bottom, heat is 23%, and of that, the heat that we use for our homes for heating and hot water is 17% of the UK's total. There's been very little progress. It's an incredibly difficult problem to solve for a lot of technical and slightly boring reasons. But with technologies like EVs, solar, offshore wind, all rapidly decarbonising other parts of the economy, heating has basically just stumbled along at the same kind of rate for over a decade. And yet on a personal level, you know, for each of us looking at our carbon footprints, not just the national view, it's a huge part of your household or of your personal carbon footprint, larger arguably than getting an EV or going vegan or flying less. Not that those things aren't important too, but it really puts it in perspective that heating is one of the single biggest contributors to our individual carbon footprints. So I know I'm preaching to the converted here though, but I thought it would be useful to kind of frame how big a problem heat is and kind of put at the outset that there's been minimal progress really in the UK to date. Given that the other speakers are representing different technologies, I thought I would touch on 4 of the key electrification of heat technologies. And that's the kind of fractious debate that I alluded to at the very top. So electrification is one pathway, sort of arguably hydrogen is another, perhaps more in theory than in practice. And I'll touch on that in a second. But what you see on the screen are the main categories of technologies for decarbonising heating using low carbon and increasingly low carbon electricity. So heat pumps of various varieties, air source, ground source, water source, communal, district, or individual. They use electricity. Fundamentally, they move heat from the environment into your property, whether that's extracting the majority of energy from the air or from the ground, and then using electricity to shift that into the building. It's the core way that heat pumps work. I'll leave my colleague to talk you through that in more depth. Typically, they've got one external unit. You need a hot water tank. There'll be a few bits and bobs around your heating system, buffers, expansion vessels, stuff like that. But it's a wet central heating system, ultimately quite familiar with what people are used to in the UK. They're very efficient, but they do work best at low flow temperatures. So a quick précis on heat pumps. Infrared heaters are another technology. They also use electricity. They generate infrared light, which basically heats the objects that it interacts with. So that energy passes through the air rather than warming the air itself. You need multiple panels around the home. They're kind of almost point of use or application specific. So they'll heat whatever is in front of them. They won't heat something in the other room. And they can be mounted on walls, ceilings. They're very flexible in terms of the size and orientation and stuff like that. And again, I'll leave my colleague to talk through their infrared option. There's then traditional storage heaters, not to be knocked. They absorb energy during off-peak periods, typically overnight, when it just so happens that electricity is low carbon. They store heat in each room and release it when it's needed. You'd have multiple around the home. And there are now smart options available. I often say that because the storage heater is a much maligned technology from the 70s and 80s. which, yes, in the olden days just basically ran out by the late afternoon, early evening. But there are very, very efficient high heat retention and smart versions available now. So there's potentially a bit of a renaissance in storage heaters. And then zero emission boilers, that's TEPEO's kind of trademark name for our technology. It's a much newer version of a solution to the low carbon heat problem than the other three that I've talked through. You can think of it basically as a grouped up set of storage heaters in one big box, like a boiler though. So it uses off-peak electricity, stores heat in a boiler in one form factor. And unlike storage heaters, connects to your existing distribution system, radiators, underfloor, whatever you've got. And again, in our case, it's smart internet connected and basically like smart storage heaters, triangulates for low carbon electricity, not just a blunt tool for off-peak. So there's a kind of quick range. There are, of course, others, and there are things that I've deliberately not put on this slide, like direct acting electric boilers, a big kettle that you bolt into your heating system, because fundamentally there are good reasons that's a terrible idea. And I'm sure there are things that I've missed. If there are questions as we go, I'm happy to try and cover them. But these felt like the main solutions that are on the table. What about hydrogen? The other half of the slightly fractious debate. Fundamentally, I don't think anyone around this table would really point to hydrogen as a realistic option for domestic heating, which is why I've put this out here, and then we'll swiftly move on. But I don't want to be completely glib and dismissive. So there are three key things that I often think about in trying to review hydrogen. The earliest estimates, even from the hydrogen industry itself, put the availability of clean hydrogen after or 2040 or beyond. So from my perspective, even if it's a brilliant idea and proves to be a crucial linchpin in decarbonising home heat, we can do something else for 18 years. And I would rather we all do that than just wait. So that's kind of almost non-arguable. I don't think anyone in the hydrogen side of this whole issue would campaign that they can get you a hydrogen-powered hydrogen boiler now. It does require a ton of electricity if you produce it in a green format. You'll often hear several different colors of hydrogen talked about: green, blue, brown, gray, there's even purple and pink. Fundamentally, green is the only one that doesn't emit carbon and require carbon capture and storage, or uses nuclear energy, which again, arguably could be best used somewhere else. So compared to a heat pump in particular, it's extremely inefficient. Rather than using 1 unit of energy to produce 3 or so, with hydrogen, you need to use some energy to split water. You then need to store that, pressurize it, ship it, and then convert it back into a grid, which then needs to be burnt in an imperfectly efficient boiler. And ultimately, with the sort of links and sources in the bottom left-hand corner, you get to the stage where a heat pump is 6 times more efficient than a hydrogen boiler. So all the costs and issues that come with that inefficiency are kind of clear. And fundamentally, if you burn hydrogen, you're still producing emissions. There's no way around the NOx. It creates local pollution. That's got health implications. Even if it is truly green and zero carbon, there are other downsides of burning stuff. This hydrogen ladder, which is a bit complicated, but I've added a link and a source in the bottom left-hand corner, tries to outline where hydrogen could play a really crucial or essential and unavoidable role in the decarbonisation of the entire world economy. Domestic heating, at least in the view of Michael Liebrecht and his team who produced this, it is way down the list. There's a million, well, not a million, there's 2 dozen better applications for hydrogen than domestic heat. And given a finite supply, we are better to deploy it there than just burn it and send half of it up the flue. So there's a quick kind of primer. I hope that was as brief as I could make it on decarbonising heat, the various challenges and options. So TEPEO, very briefly, we're a UK-based startup now, kind of scale-up, based just outside of Reading. Founded in 2018, and since then have basically been developing our zero emission boiler. I will from here call it the ZEB, ZEB, as a solution to low carbon heating that works in a very different way to the other options that have historically been available to the UK. So this is kind of it. You can see from the 2 tailpipes at the back, it's a boiler. Effectively, there is a flow and return pipe at the back and a power cable to bring power to it. It's a very, very simple machine, but what that allows you to do is basically have a kind of plug and play, a drop-in replacement for an existing boiler. The way it works is that we have 40 kilowatt hours. So if you think of a small, medium-sized electric car battery, or 3 Tesla Powerwalls, or I don't know, something like 5 or 6 maybe hot water tanks worth of storage capacity, we charge that up with a 9 kilowatt electrical input with basically heating elements that supercharge or heat up a ceramic thermal core. And then we deploy that heat, as I said at the start, to your existing distribution system. So if you have radiators supplied by micro-bore thin pipes, and they're high temperature radiators, and replacing all that stuff is tricky in your particular case, the ZEB is a brilliant solution because it can just operate with high grade heat. The material doesn't degrade, it's non-toxic, it's not like a chemical battery that will lose capacity over time. Fundamentally, not to sort of do our product a disservice, but it's a big hot rock, and there's very little that can go wrong with that format of technology. We just heat it up and cool it down again. We have a ton of electricity monitoring I'll come on to briefly that lets us do some quite clever things with helping the UK electricity system deal with an increasingly renewable and intermittent supply of power that makes the ZEB low carbon, in addition to being zero emissions at point of use. And we can use local generation sources, solar on wind turbine, and sort of match low carbon generation to the ZEB's power consumption. All those things roll together, make it low cost, low carbon, and it's a smart product with a customer app that lets people control various factors of how it works. I'll breeze over this, but I don't want this to be a sales pitch. I want to try and talk through how these products work so that you may be able to apply them to other similar technologies. Fundamentally, we've got the hot core at the top, and this is deliberately cartoony to protect our IP, but we blow air up through the core. That captures heat as it passes down through the core again into the base of the ZEB. You can see the red arrows coming out the bottom right-hand corner, and that passes hot air over a heat exchanger. Operates exactly like a boiler, but instead of combusting a fuel to produce hot gas, we pass air over our hot core onto the same type of air-to-water heat exchanger as you might find in an oil or an LPG or gas boiler. We then rinse and repeat that process round and round to deliver heat out to the heating system. The smart side that is, as I mentioned, more about also supporting the UK electricity system. So every home is different. Every home uses heat in a slightly unpredictable and chaotic way. So we have a bunch of sensors built into the ZEB and IoT, Internet of Things, cloud-based technology that basically takes weather forecast information, a thermal model of your home and how you use heat, the carbon intensity of the UK's electricity system. There's more coal and gas. We'll try not to charge the ZEB until there's more wind and or solar available in the shoulder seasons. And we merge all that stuff together with your particular tariff, a bit like a storage heater. This product works best where you have an off-peak price and a sort of peak price, and you basically triangulate and focus in on the cheapest electricity to charge the ZEB and then deliver heat sort of separately. So these moving graphs are basically what's happening inside a ZEB's brain. It's automatically repeat calculating what's the cost optimal route and carbon optimal route to meet a customer's forecast heat demand, given the price of energy. So you can see the top graph is basically filling up when the dotted line, the price of electricity, is lowest, and the graphs in the middle at the bottom are overlaying solar availability to that same calculus. Does this in real time, basically every day throughout the day, and as things change, as the carbon intensity or your heating use in your home changes, recalculate and figure out when is the sort of next best or the currently best way to charge to meet a forecast heat demand. What all of that means is that the ZEB is a potential linchpin in the UK moving to variable sources of generation. So as we onboard as a country more and more wind energy, solar energy, tidal interconnectors to the likes of Norway all the way down to Morocco, we will have an increasingly volatile system that basically has peaks and troughs of supply and peaks and troughs of demand. And devices like this that can basically scatter around and pick the lowest carbon electrons and make sure that if there's wind available, we're using it. And if there isn't much wind available, we can turn down our services. Helps actually deliver a low carbon electricity system. Without a lot of flexibility and storage, the UK electricity system fundamentally cannot get to a kind of net zero electricity grid. You need flexible demand if you're going to have more and more and more flexible supply. couple of little examples I thought might pique people's interest of what that looks like in the real world. On the left-hand side, with our monitoring, and other technologies do the same: smart hot water tanks, smart storage heaters, home batteries. Again, I don't want this to just be some kind of jazz hands about the ZEB. There are lots of things that can do this, but ZEBs replicate the same model. On the left, you've got frequency monitoring. This is the fastest reacting, often sub-second responses to changes in how the electricity system is balanced. If it gets out of balance, we get blackouts. What you can see here are two examples of a North Sea interconnector tripping and the frequency dips. And then the same thing with the two nuclear reactors at Sizewell A and B. They trip and frequency dips. When that happens, you need services to turn down. And the same thing can happen in reverse. Frequency can spike if there's an excess of supply. And yeah, so the ZEBs can play a role. You know, you can just use your heating as you want to in your house. And if the ZEB's kind of flicking on, flicking off, you know, and dynamically adjusting when it's charging or not charging, it can play this balancing act and support the UK energy system in onboarding more of this renewable generation that kind of creates problems if you don't have flexible assets at the end of it. On the right-hand side, you've got a view of the balancing mechanism, how the UK effectively pays renewable generation to turn off is the kind of glib summary. The more wind we have available, the more often we will have times where there's nowhere for it to go. And the best thing you can do at that point, you still have to pay the generators. There's a kind of minimum that they've contracted to participate in the UK energy system. And ultimately then, as bill payers, we all end up paying for renewable power to not be available, which is insane. It would be far better to have somewhere to put it. And ZEBs can play a role in doing that. Some example installs. The top right is a hideous picture, but in someone's garage. We've also installed them in flats. It's a useful part of our technology that there's no flue, so it can go on an internal wall. It can go somewhere that boilers can't. If you can't get a gas supply, you can't get a flue routed from it. It can also go where heat pumps can't. If you haven't got any outside space, well, this is a really good option because it can, well, it goes inside your property. So yeah, there's just a few examples of the ZEB in situ. It's, like I say, a bit of a drop-in replacement for an existing boiler. Slightly larger, but operates in the same kind of manner. And yes, if you want to find out any more, then tepeo.com. There's a sign-up page. There's a bunch of information about us and our product. We also have an episode with Fully Charged, who I guess a lot of people in the school might be familiar with, but YouTube channel, media company focused on low carbon technologies in general. And in their Everything Electric channel, we've got a good 15-minute interview with Tepeo CEO talking about our technology and basically going into more depth about all of this than I've just done. But yeah, I hope that was useful. I also have no idea if I kept to time, so Lindy, I hope.
Oh, we're not doing too badly, Ian. Thank you, because you took a bit of the time for the introduction and a particular and great thank you for that overview about why we need what we need. And certainly, I think for most of us, the ZEBs was the newest of the technologies that you know, we've heard about infrared as a theory. And we've heard about heat pumps, but I think that was a very interesting move forward. I've seen some very sophisticated questions coming through there. Ian, if you want to stop sharing your screen,
Sure.
And Sean, do you want to pick through some of those questions and see whether you can find something which is perhaps the most straightforward to answer at the moment? But we've got about 5 minutes for the questions at this point, or slightly over. Thank you.
Yeah. So Eleanor asks, has off-peak electricity made a comeback recently? And do all suppliers offer that at the minute?
Yeah, good question.
I think you're frozen there, Ian.
Reference point. The main tariffs that those have their go, EDF have something called 9.5, British Gas have something similar, but they are intermittently available in the current energy market. So yes, they have made a comeback with EVs and then Ukraine. There are still tariffs available though. So yeah, most of our customers are on something like an EV tariff.
Okay. And then Jenna asked the question, how does burning hydrogen produce NOx?
God, that's a good question. You're not speaking to a chemist. I don't actually know. I would guess some form of imperfect combustion just creates NOx as an output. I don't actually know. I just know that combusting hydrogen rather than putting it through a fuel cell does produce NOx and other particulates. So some kind of imperfect combustion, but yeah, I'm not a chemist, sorry.
Is the nitrogen in the air, by the way?
Thanks. I'll bank that and remember it.
Okay. Janet also asked, how does the cost of the ZEB compare with a new conventional boiler?
Okay, yeah, so up front the ZEB is 6,000 including VAT, which if anyone fancies writing to an MP, is something we are campaigning to have changed. We don't attract a 0 rate of VAT, so that's with 20% added. We are looking to drive down the cost, but we are a small UK company, not yet operating at huge economies of scale. So 6K including VAT, it's typically about a day, day and a half to install. So local labour rates vary, but that's the upfront cost. It's probably roughly double a gas boiler, and depending on what you're looking at with oil and LPG, a bit more than those systems. But yeah, more competitive versus oil and LPG than just grid gas.
Okay. And David asked, are higher thermal energy storage capabilities available, capacities available?
There are companies I'm aware of, one in particular called Caldera that operates a similar technology to Tapio on a bigger scale. But otherwise, no. I mean, it's very, very hard to store that much energy in a small footprint. So other technologies that use phase change or battery chemical storage, electrical storage, typically they're vastly lower in the energy stored per meter cubed or per kilo than the ZEB. It's taken a lot of R&D to get 40 kilowatt hours in the footprint, roughly the size of a freestanding fridge or a washing machine type volume.
So could somebody actually use 124 hours a day for the heating to be left on?
Yeah, so
charging up.
Yeah, we have an upper limit of the heat demand that the ZEB is really designed for. So up to about 12,000 kilowatt hours of gas, 1,100 litres of oil, that kind of fuel consumption over a year. And the reason for that is that up to that level, we get a good ratio of off-peak charging, filling the majority of your heating demand, to top up peak charging in the coldest weather, which is obviously expensive and to be avoided. If we deploy ZEBs in massive homes with really high heat demand, then it'll charge overnight, discharge immediately in the morning, and then just have to charge all day. And back to my point about direct electric boilers just being big kettles and a bad idea, that's kind of why. So we have a sort of medium-sized home downwards ideal operating range to make sure that ratio of off-peak to peak energy gets you to a reasonable running cost, not dissimilar to fossil fuels in the running cost.
Okay. And then Sean asked, what are the dimensions of the ZEB? And Laura asked, what are there any restrictions on where it can be installed in terms of space and ventilation? And am I correct in thinking that it has to be installed on a concrete surface?
Great questions. Someone's done their research. Yeah. So the ZEB is 60 wide by 66 deep by 98 high, I think. So basically a freestanding fridge. If I've got that wrong, they're on the website. In terms of ideal locations, we do need some ventilation, but you're literally talking, if you box it in a cupboard, cut some air channels at the top and bottom just to allow air to circulate in case heat builds up. But no, we don't, there's no like active extraction needed. And in terms of location, yeah, it's a heavy object, so it does need to be ideally ground floor mounted. And yeah, a solid base at that. Doesn't need to be concrete, but does need to be a stable floor surface.
Okay.
Why I've gone so blurry.
Okay, that's brilliant. There's bound to be more questions, and I'm seeing more questions appearing there. I mean, either Ian, if it's appropriate, you can answer there, or we'll pick up questions at a later stage. And look for answers and post them up on our website. But thank you so much for taking the time to introduce that. I can't pretend that I understood every single bit of it, but it has piqued my interest, as I'm sure that it needs to do as an alternative. So that's absolutely brilliant. Thank you very much. And can we, I'd like now, please, to welcome Adam Broadbent, who has come to us from Herschel Infrared. Are you there then, Adam? I'm not seeing.
I am, yes.
Yeah, there you go. There we are. Lovely. Thank you. So fantastic. Adam, thank you very much. I know that you picked up this later because you are Leeds based, I think. So this was, I understand, the chosen heating solution for a zero carbon house at COP26 last year. So that's an interesting little tidbit to dangle in front of us as well. So looking forward to hearing what you have to say about the way the infrared heating works too. So thanks very much.
Perfect. I'll be 2 seconds. I'll get my screen going, and then we can start. Right. Here we are. Right, so my name's Adam Broadbent. I'm based in Leeds. I work for Herschel Infrared, and I look after the north of the country. Our offices, our warehouse, our main stores is all based down in Bristol. Product that we're offering is infrared heating. I'm sure you'll have seen different forms of infrared over the years. Traditionally, most people know about shortwave infrared, which tends to be outdoor heaters. There's also medium wave, and there's also, which I'll touch on as we go. So I'll just jump in. So the major form of infrared that we would be suggesting for domestic properties is our range of panels. The way and the reasons that they differ from most forms of technology and heating that you'll have seen previous. Most forms tend to be convectional. So it's hot air circulated in a cold space. And the way that the infrared panels differ is that we're actually heating the thermal mass of the property. So the panels are radiating heat onto surface. So what that means is we're heating the walls, the floors, the ceiling, any objects in the space, any people in the space. And it's actually the oldest form of heating. It's the same way the sun heats the earth. So the infrared heat comes down, it heats the land mass, and then the air temperature increases because of it. And it's the reason why we've got a nice little picture there of some people waving their hands on a ski slope, because even though with all that snow and frost it's absolutely freezing, the infrared heat from the sun is actually warming the space. So if anyone's ever been skiing, snowboarding, or been out on a very cold day gone sledging, it's the reason why you do still feel warm. Obviously, it's heating thermal mass. So the easiest way to describe that, which I find people understand best, is it's almost like heating water in a pan. So what you're doing is you're heating the pan, and then the water inside is increasing because it's warming because its surroundings are warm. So that's what we're doing. We're heating the walls, the floor, the ceiling. This will then increase air temperature. Because we're heating in this way, it means that the room stays warmer for a lot longer. We use a lot less power to achieve this. It's all monitored by thermostats like you would with any other form of heating. But it means that once we achieve temperature, we don't have that constant surrounding cooling effect working against the hot air that you produced. Because in rooms like bathrooms, in rooms like cellars, where things like damp, mold and mildew, which have obviously been in the news recently, can be an issue. Infrared is actually really helpful with this because we're not circulating hot, damp air onto cold surfaces. So obviously, if you were looking at something like a bathroom, you would still pair it with ventilation. But because we are heating the surroundings, things like damp, mold, mildew, you're not going to get them. We're not circulating dust because we're not moving air. We're not circulating dust. We're not circulating bacteria. So it does help with those as well. Excuse me. The major form of infrared that we're talking about with the panels is far infrared. So that means that there's no light and no sound. The other spectrums I'll touch on quickly. So shortwave is the traditional outdoor heaters, which tend to be quite bright light, which is a very intense heat over a very, very small distance. You then move into the medium wave spectrum, which is more of a warm glow. It's not as an intense a light, and it covers a larger area, but less intensity of heat. And then obviously far wave, which is the panels that you would use in the domestic. Right. It's massively improved the comfort of heating. So I'll touch a bit more on that as we move on to the next slide. But it's more a case of the feel of infrared. So I've got a little diagram there just to show. So obviously we're all radiant beings. If you were to walk into a cold space, so if you've been out on a warm day and you go inside and it's cold, the room is actually taking heat from your body. So it shows that he was nice and warm, but he's gone into a room with surroundings that are cold, so it's taking the heat from his body. And we go to the next where you can see that he was colder than the environment that he walked into, so he's actually taking heat from the room. And that's basically how the comfort levels of infrared work. And you will find with infrared as well that lower temperatures tend to be more comfortable. And again, it's just the fact that there's no cold surround. So that, another way to explain it, which works quite well, with traditional forms of like radiators. So let's just say in your living room, you would probably have a radiator underneath the windowsill, and you'd probably have your sofa pushed up against it. So you might, using something like a gas combi, you'd heat the room to 21 degrees, so you were nice and comfortable. But if you then sat on the sofa with the back to the cold window, you would still feel the cold. And that's the way that infrared helps, because we're heating everything to raise air temperature. I'm going to try and on this just briefly. So this was an independent study that we did with the university, and it was basically just looking at other forms of heating and how they compare with the likes of infrared. So we were looking at electrical conventional, we were looking at heat pumps, and we were looking at infrared. So as you can see there, we were looking at the lower temperatures, because the comfort level, you don't need to get the air temperature as high as with infrared. Obviously, if you look at the efficiency, the heat pump does win out on efficiency. So when we talk about things like coefficient, you might say that a heat pump uses a kilowatt of power, but gives you 3 kilowatts worth of hot air. Now, it differs per property, depending on how well insulated it is. It differs on the heat pump, which I'm sure my colleague will talk on next. The only real key thing I want to touch on this, obviously, because we do have somebody talking about heat pumps as well, is that from some of the examples and some of the customers that we've worked with, the initial investment that was required for the heat pump was significantly more when we were looking at the infrared. And what we've been suggesting to customers was rather, excuse me, was looking at using the additional money saved to increase the insulation of the property, because the more it's insulated, it means that we're using you're keeping the heat a lot better. And then we were also looking at offering it with something like solar and battery, so that that's adding to the offset of the bills as well, which all improves on. So I don't want to touch too much on this, just obviously with somebody here to talk about heat pumps as well. We've got a couple of examples. So with the panels that we offer for the domestic, they can be ceiling mounted, they can be wall mounted. It's very important when we talk about wall mounting, we're not talking about hanging them like you would a traditional radiator, either a wet system or a conventional system. You wouldn't have them at low level. You would hang them like you would a picture or a mirror. I have blurred my back, but I don't know if you can see there's a little white panel there in the middle of my wall just there. So that's a little infrared panel, and it sits at midpoint, just like you would a normal picture or a mirror. And that's heating the thermal mass of the room. So as you can see in the picture, we've mounted there on the ceiling. The image on the right was for the COP26 house in Glasgow. Again, it's literally just the 2 panels that you can see on the ceiling that heated that entire space. These are a bit more commercial, but I just wanted to dive into them while I'm here. So on the left, that's the Summit. It is far infrared, just like the panels, but with a commercial space like that, because the ceilings are much higher, it makes more sense to keep the heat more localized. So we've got the heaters lower down, so we're not adding all that hot air to the top of the room. I'll stay a bit clear of this because I don't want to dive too much into the commercial side. Again, a bit more commercial. So the heaters on the left, they are medium wave. So it's a light emitting heater, which means it's a lamp rather than a ceramic heater. And on the right, that's our new Halo heater, which is far infrared, pretty much designed for churches. And with the infrared panels, we have a lot of different types of heaters. So you don't just have to have a plain white panel. You can provide an image and have it printed on to look like a picture. You can have a mirror, which is ideal for bathrooms. With it being a heat source, it won't mist up as well while it's heating the room. We do the portable versions for those that are looking to just trial it rather than, taking the plunge and heating the whole house. And the towel rails for the bathroom again. I'm a big advocate for infrared in bathrooms, especially because those are the rooms that tend to be quite hard to heat, and when you do, again, you're circulating hot damp air, so you do tend to have things like damp, condensation, mold and mildew, and this is where infrared really does make a difference. We're on with a lot of social housing and councils at the minute, especially after the news with the incident that occurred. So there are a lot of them that are looking at new solutions that we can definitely play a part in and make an impact. It's not just infrared, it's not just the other forms of technology. It's really important in how you control that. And I'm sure the other gentlemen will be on my side with this. Any form of heating can be efficient, but it's really down to how you manage and how you control it. One of the things that we push for with infrared is we sort of got stuck in the way with gas combi systems, that gas was so cheap, we didn't really mind the implications it had on the environment. We didn't really mind that when you turned your thermostat on, the whole house heated at the same time, even though potentially you might only be using 1 or 2 rooms. So with infrared, we do really push for individual room control. So like myself now, I'm in my office, I'm only heating 1 room out of my whole property, rather than wasting energy on the rest of it when it's an occupied space. So I won't delve any deeper into it. But that's pretty much my presentation there. I think I've gone a bit over, so I am sorry.
I think well, only by about 10 seconds, Adam. So I think you've done brilliantly there. So.
I was trying to keep a timer, but I didn't want to step on anybody's toes.
Well, that's absolutely brilliant. And I saw some questions coming in as well. I think certainly I'm picking up from that around the lots of things for us all to think about in terms of the specifics of our own home and the way we use our home and so on. Sean, do you want to pick up some of those questions?
Yeah, sure. Sean asked, how does this system compare to conventional radiators in terms of heating costs? And sorry.
No, it's all right, you carry on, Sean.
And then he also asked, does this system also produce hot water for the home?
No, one thing we're a big advocate with Herschel is that we always recommend having your heating and your hot water separate. If there was ever a failure with a system that was both, then obviously that's your heating and your hot water done. You've issues until it's repaired. With infrared, if you ever had a fault with the panel, it's 1 room. The rest of the property still works. There are options for the hot water side, but we don't deal with anybody specific. So I don't really want to name drop companies. We do deal with some companies that we recommend. I would probably mention names in a more private setting than I would, shouting the names out in a group like this. What was the other one? Sorry, Sean.
And how does it compare cost-wise to a conventional radiator? And I guess like a gas system.
Yes, I mean, this is the bit where it gets a bit tricky. So if you were to compare it to a gas system, with most gas systems, you're heating the whole property. So if we were to heat the whole property with infrared versus the whole property versus a gas system, the gas system would be cheaper, purely on the price difference between gas and electric. But what I do with my property is I've zoned every room as its own individual space. So like now, I'm in 1 room. I'm heating this 1 room with 600 watts. So that little panel behind me is 600 watts. That's where I become more efficient, and my energy costs are a lot cheaper because I'm not wasting energy on an unoccupied space. But whole solution versus whole solution, gas electric, unfortunately gas is cheaper, but it's not the most efficient way of heating.
Okay, thank you. And John asks, do you still need to ventilate rooms, e.g. converted basements or bathrooms?
I would still advise bathrooms definitely for ventilation. The room I'm in at the minute is a basement office, so I'm in a 3-floor terraced house. The office that I'm in is below ground level, so on this side it's underneath the garden. This side is underneath the garden, and then the side over here is onto the garage, which is uninsulated. So ventilation in this room, not so much of an issue, but whenever it would be a bathroom, we always would advise ventilation, which with any form of heating, it should be ventilated in the bathroom.
Okay, thank you. And if you want to quickly boost the temperature of a room for 30 minutes or so before sleeping, can you do that without changing timers, etc.?
Yeah, of course you can. You can do it through the thermostat, or we use the Smart Life app for most of our thermostats. So you can do it through your phone, through a tablet, through a desktop, or you can just physically walk up to the thermostat and boost it to whatever temperature you would like.
Yeah. And then John and Susan, I think, asking similar questions. How long does it take to heat up a room?
It would depend on the method of how you heat the room. So there's the two main ways I recommend heating with infrared. You can run it like every other heating system you've ever used, which would be in the autumn and winter, depending on the temperature of the day, would depend on how long it takes to heat up, like any other form of heating. The way I run my system, which is a lot more efficient, is I set a background temperature in every room of 10 degrees C. Almost like a frost setting on the boiler. Now, it would have to get to about -3 outside before my internal air temperature drops to 10 degrees C. So realistically, it never does. So I'm never having to do that. So that then when I want to get to room temperature, it's a much quicker process. If it did have to top up at 10 degrees, it would be using very little power.
So how long would that take to?
So for me, I'll give you an example. I in this room to get to 21 degrees, I would be looking at about 20 minutes.
Okay.
So again, it's just going to depend on how well insulated the house is and what temperature you want to get to.
Okay. And how much does it cost to install a system like this if you're going to put the panels on the walls? Does it cost more to put them on the roof? Do you need more structural components?
It would depend on the age of the property and access available. So if it's a more modern property with plasterboard ceilings and roofs, then it's quite a quicker process. If it's an older property where you might have to go into the floorboards, possibly in the room above, it would just depend. But I'll sort of give a bit more. So most sort of modern 2 or 3 bedroom properties, you're probably looking at somewhere between sort of 3,000 up to maybe £5,000 for the panels, thermostats, and then the installation on top is just going to come down to the area that you're in, and it's going to come down to the rates of the electrician that you're using. I've just done a project the other day which was for a 2002 built 3-bedroom house. The panels came in at about 3,200 and the installation was about £1,100 on top of that, and that was for 2 days installation. So it's every property is different. We offer a desktop service for specifications, so either we can email you a survey form, we can, if you've got floor plans, if you've got your EPC, we can work straight from that. But we've got a good team of internal surveyors that can really assist with specification, and it's completely free.
Okay, thank you. And Jamie asks, does it have a boost feature so it will turn itself off after a certain period of time?
It would depend if you've got a program schedule in place. So most of our thermostats, most thermostats out there tend to do 4 settings a day: morning, afternoon, evening, and overnight settings. If you were to boost, let's say you boosted between morning and afternoon, it would either stop when it achieves temperature, it would stop if you say boosted it for an hour, or it would stop if it hit the next schedule. So it all depends on when you boost it in your schedule.
Okay, thanks. And Corrine asks, what is the carbon footprint compared with gas central heating?
Sorry, Sean, you went a bit fuzzy then. Could you just repeat that, please?
The question was, what is the carbon footprint compared with gas central heating?
Yeah, so our products are 100% efficient. It's all going to come down to how you're getting your energy. So it's pretty much like most forms of energy efficient heating out there. It's going to depend on whether you're getting your power from solar, from wind farms, or whether you are from fossil fuels. And
what happens when the products become end of life? How long do they last, and can they be recycled at the end?
Yeah, so at the minute, our products are about, we'll have to spout this off the top of my head, I'm sorry, I think it's about 90% recyclable. We are pushing to get to the full 100%. Depending on the range of heaters, we've got 2 of the panel range. One's 5 years warranty, one's 10 years warranty. With the infrared panels, there's no mechanical moving parts, so they don't have to be serviced every 12 months. So realistically, they can go for a very long time. For an example, I've had panels in my property now for 6.5 years, and I've not had to replace any of them. We used to do the NSBRC self-build show, where we had panels on a stand that would turn on all day long every time the lighting for the building was on, and it's a 18 hour 7-day a week exhibition centre. So those heaters were constantly on for about 6 years straight, and we never had an issue with any of them.
Okay. I think people probably aren't used to infrared technology, so is there anywhere where people can go to actually experience what it's like?
Yeah, I mean, the best place to go, unfortunately for probably a lot of people in this group, would be Bristol, which is where our showroom is. It's not just the showroom, the offices are all heated with our panels, with our space heaters, the bathrooms, the kitchen, the corridors. So it's a bit of a living model plus a showroom that demos everything. At the minute, I am currently trying to establish the exact same thing up here in the north, in Leeds, local to where I live. I mentioned it to yourselves earlier, but it's just proving a bit hard at the moment, as you can imagine, in this current market, to try and find the right location to do this in. We can recommend a lot of commercial places to go look at our products, but unfortunately, the heaters that you'd be viewing are slightly different to the type that you would see in the domestic market. But please feel free to get in touch with us. If you look on our website, herschel-infrared.com.uk, you can contact us on most social media. I can pass over the details for domestic case studies. I can put you in touch with customers like yourselves who've installed our panels. Quite a few of them are open to things like this. They'll do video chats, they'll walk you around the home, show their experience, the running costs compared to what they used to have, return on investment, things like that. I don't want to go too far into it, but we're here to assist and offer as much information as we can.
Thanks so much, Adam. And again, I would ask actually for all of our presenters just to drop their website addresses into the chat, just to pick that one up again. So thank you, Adam. That was really interesting and feels sort of manageable, and that was definitely alternative. Do you want to stop sharing your screen now? And
yeah, of course I will.
If you don't mind just waiting for a little bit and see if other questions come up. But meanwhile, it's going to be welcome to Robert Stibey, who is joining us from, I think you're down in Bristol, aren't you, Robert? And you're from Daikin Heat Pumps. And I know that the heat pumps are something which is an alternative technology that we have all heard of more. We've heard a lot more about than we have the infrared heating or the zero emission boilers. But I think it would be very helpful to all of us if we have that opportunity to move on and to hear a little bit more about it. So are you there, Robert? Are you going to?
Yes, can you hear me?
Yep, can hear you and see you. And I hopefully we can share your screen as well. But thank you very much for coming along and being here and ready to tell us the bits and pieces about the heat pump. So thank you so much.
No problem at all. All right, 2 seconds, just share the screen. There we go. I hope everybody can see that. Linda, if you mind confirming, sorry.
Yep, we're fine. Yep.
Brilliant. Okay, so I work for a company called Daikin. I worked for Daikin for just a few years, and it still surprises me every single day how many people have never heard of the name Daikin. Or even necessarily what we do. Just a very quick sort of brief background. We are now the world's largest air conditioning manufacturer, and now I've sort of possibly pointed this out, as you possibly walk around shops and banks and other such leisure facilities, you will spot the air conditioning in those places, and you will see the Daikin logo over quite a few of them, to be honest with you. Now you've heard of us, like I said, you start spotting us around a lot more. I wanted to just say a couple of things because I've just said air conditioning, and it's not actually truly air conditioning. Air conditioning would mean changing the temperature, the air quality, and the humidity. So normally air conditioning is just used as maybe a bit of a slang within the industry when we talk about air conditioning. It doesn't necessarily mean complete air conditioning. We're generally just talking about being able to heat and cool a space. Moving on, I wanted to just mention then heat pump. So what's a heat pump? Well, a heat pump just basically means a system that can do cooling as well as heating. Effectively, that's exactly what a heat pump means. To be more specific, we also then talk about things like ground source, which will take the heat from the ground, and air to air, which is actually really the properly commonly known air conditioning unit, and air to water, which is what we're all really here to sort of, or what I'm here to discuss today anyway. I just needed to give you a little bit of a background about this and some of the fundamentals. Some of these you hopefully remember from your old science days, but it's just nice to understand some of these principles and how long it's actually this sort of technology and stuff's been around for. So actually heat pump itself has been around since the mid 1800s. A modern air conditioning system, air to air system, been around since the early 1900s. Mainstream heat pumps has been around since the 1950s. So this is not new technology at all. This has been around for a very long time. Just to explain these sort of fundamentals, I wanted to sort of mention, so you get this sort of background and you'll understand why a bit more in a second. There are all other videos you can also see online if you want to. Fully Charged, I've actually got a really good explanation recently about heat pumps, and also Heat Geeks as well. Okay, the sort of fundamentals I want to talk about is just point one, possibly not so important from my explanation about how a heat pump works, but this is good to know. How does heat transfer? If we use hot air for this example, this will have lots of agitated molecules, as you can sort of see in the picture on the left-hand side. These agitated molecules actually want to transfer to the least agitated molecules, cold air. So hot air effectively transfers to cold air. The second point I want to make, and hopefully you all do remember this from your science days, that pressure and temperature is related. So if you increase the pressure of something, you're going to increase its temperature. Same thing again, you decrease the temperature in something, you're going to decrease its pressure. And lastly, point three, which actually follows on from point two effectively, as this also means you can change a liquid's boiling point. For this example, if we boil a kettle of clean water, it will boil at 100 degrees C. But actually, this is a atmospheric pressure, which is 1 bar. So if we were to climb to the top of Mount Everest, where the air pressure is much lower, it will lower the boiling point of water. And if you're interested, that's about 68 degrees. So you can imagine that's a lot cooler than 100 degrees. Modern day heat pumps use, actually the best way of explaining it is a very high efficient heat transfer fluid. I'm gonna just say refrigerant because that's what it's commonly known as, but really it is just a super high efficient heat transfer fluid. From the picture you can see on the screen, hopefully, number one is the compressor in the middle. I'm just going to go through the cycle, so hopefully you get a bit more of a better understanding of exactly how this works. All this compressor is doing is compressing the refrigerant. Yeah, so when we compress the refrigerant, effectively we're increasing the pressure. And as I mentioned in the point two previously, hence I've needed to tell you these fundamentals, we're going to increase its temperature. So we will now have a hot gas and high pressure. This passes through the plate heat exchanger, number two. On the other side of this plate is your central heating water, when we're talking about an air water heat pump system. If you were talking about an air to air, effectively, we're not passing water to the other side of that plate heat exchanger, we're passing air across the other side of that heat exchanger to warm it or cool it. But in this instance, we're passing that water through that heat exchanger, which is going to absorb the heat from that water, from the refrigerant, sorry. At this point, this heat will then transfer to the water as it's cooler, in turn removing the heat from the refrigerant. This will convert this high pressure, high temperature gas into a high pressure, slightly cooler liquid refrigerant, or high efficient heat transfer fluid. We now need to change its pressure to be able to boil off the liquid. We do this with a device called an expansion valve. Effectively, we expand the refrigerant, but to make it a lot simpler, you can imagine it as a tap, and we can open and close this tap to cause a restriction within the system. Now, when we cause this restriction within the system, it's still going to stay a liquid. It will drop in temperature slightly because we're going to decrease its pressure. And that's the main point. We want to decrease it to a much lower pressure now. Now we've got a lower temperature liquid refrigerant. This passes through the outdoor heat exchanger, where it's warmer than the refrigerant. All we actually have to do with this liquid refrigerant is actually boil it off. So if the pressure's right for this very efficient heat transfer fluid, we can then boil it off. And as it's doing so, it's absorbing heat from the surrounding area. Once we've got that gas, yeah, we can then, it will then come back into the suction side of the compressor, well, where everything will then literally just start again. Now, there's two things I want to mention here. So the most common question I get asked is, how can you still take heat out of the air when it's below zero? You might have seen the bottom left-hand corner of that slide. There's energy in the air all the way down to minus 273. So for us to take energy out of the air down to minus 25, it's not a problem. We can easily do that. And all we actually need to do is just boil off that refrigerant. There was one other little thing I just want to comment about, and it's more about where the heat is coming from. So a lot of people will look at this system and they're saying, well, all that heat's actually coming from the compressor. No, the heat is coming from where we boil off that refrigerant, and it's absorbing the heat from the surrounding air. All the compressor is actually doing is upscaling that heat effectively, yeah, to actually then make it usable inside. There is always losses in any machinery and electronics, like your phone, mobile phone, your laptop. Use it really hard, they become warm. It's the same with these devices. The compressor will become warm. The PCB that drives that compressor will also become warm. As we're increasing, as we're always trying to increase our energy efficiency and improve our technology, we now harness these heat. So the heat in the compressor actually also goes into refrigerant. So there's very low losses within the compressor. Excuse me, the heat also within the board that drives this compressor. This is now also absorbing a lot of our newer systems. We actually run a refrigerant pipe over the PCB to actually help keep the PCB cool. But that heat is then going into the refrigerant, which is in turn then heating your property. This might be going a little bit too complicated, but I wanted to explain this, and it is exactly how the heat pump is working in the background. This is a pressure enthalpy chart. In that same cycle I showed you on the last slide, we have the compressor on the right hand side. We have the indoor heat exchanger effectively, that's the condenser at the top. The expansion is that tap that restricts the refrigerant, as I mentioned, and then the evaporators at the bottom. It's just then going to evaporate that liquid back into a gas again. So efficiency is determined by the temperature difference between the condensing and the evaporating temperatures. Condensing being the water flow, as I just mentioned, and the evaporating as the high as possible, but is the outside ambient, obviously. The closer these two lines are effectively, or the closer these two temperatures are, is how we increase the energy efficiency on the system. This is how we can calculate the energy efficiency of the system. And it's all about trying to keep these lines as physically close as possible. Now, if we look at the outside ambient temperature, with an air-to-air heat pump, there's nothing we can do about the outside ambient temperature. It is what it is, so we can't really do much about that. We will always try and keep the evaporating temperature above zero, because as soon as we go below zero, after a certain amount of time, we need to defrost that outdoor heat exchanger, which does happen from time to time, but like I said, we're always trying to sort of keep it above that temperature if we can. But what could we do with the condensing temperature? As I mentioned a second ago, this is your water flow temperature. So the lower we can reduce your water flow temperature, the more energy efficient the system will become. And this is the same for any air-to-water heat pump system. It's not just specifically a Daikin, it's literally every single system. And also the same with an air-to-air system, effectively. So for us, this is the most important thing for us is to have the largest heat emitter you could possibly have. Yeah, the more surface area that heat emitter has, the easier it is for the heat to transfer, and the lower the flow temperature is from the heating system. And like I said, I keep saying this, the lower we can get the flow temperature, the more energy efficient it is. But this goes for pretty much any heating source as well that's using a conventional radiator underfloor heating system. Generally, the lower the flow temperature is, the more energy efficient it is. And not a lot of people tend to talk about this, but even if you've got a condensing gas boiler or an oil condensing boiler at home, I've been sort of saying, well, if a heat pump's out of your range, look, see what else you can do within your heating system to get yourself prepared for a heat pump system, which potentially may come in the future, and it'd be inevitable. And secondly, actually save yourself some energy emissions and energy usage from actually increasing the size of these radiators. Because if you can reduce your flow temperature down on your boilers, to actually get them to condense a lot more, the more energy efficient they become. Something that actually come to light more recently that somebody done a video on is they needed the flow temperature. I think it was slightly less than 45 degrees flow temperature from a boiler to actually gain the stated efficiency from it. So that kind of gives you an idea. Once you're actually flowing at these sort of temperatures, we can easily run it on an air source heat pump. So sort of moving on and trying to explain this as best I can. COP means coefficient of performance. This is just a means. This is just means for measuring the power input to the power output. So if the device would consume 1 kilowatt of electric and it was to produce 3 kilowatt of heat, yeah, basically we then have a COP of 3. Effectively 1 in and you get 3 out. If we measure that COP throughout the year, we then get something called what's called the seasonal COP, and this is literally the overall efficiency of the whole heating system. And if you guys are ever interested in air to water heat pump, sorry, this is something that will keep coming up. So I wanted to make sure it was really clear what that actually meant. I'm not going to go into this on the slide. I think it's going to be available as a handout, so you can have all this information. In the handouts as well, I've also got some data about where this information is also sourced. But I want to just give you an idea of the emissions from a heat pump or from electric for this instance. So if we were looking at the electric supply from the grid, this is data taken from 2019. We can actually see it potentially the emissions are actually lower. This was 2020 data from the national grid, but I'm going with BEIS data, which is what generally the accredited data we would look for. So this is the amount of CO2 being produced per 1 kilowatt of electric. And if I just go down to the second line, you can then see 0.185 kilograms per kilowatt for oil, for gas, and then oil is being 0.245 kilograms per kilowatt hour. What does this actually mean? Well, to be on a par with gas, we must ensure that air source heat pump is absolute minimum of a COP of 1.5. So you're putting 1 kilowatt in, and we're getting an absolute minimum of 1.5 kilowatts of heat out of it. This would be determined as actually a really bad COP, to be perfectly honest with you. And what you would want to look for achieving is a minimum of a seasonal COP of 3. Yeah. What this would actually mean in CO2 emissions, well, if we're actually taking the 2019 BIS data, this would basically mean it's half the amount of emissions whilst comparing it to a gas boiler. Obviously, as the grid becomes greener, this is also going to improve. And there's also things being called about demand side response, where the grid will actually be able to turn down your heating system when it's particularly high in emissions or very costly. So there's a lot of things coming our way. To be honest with you, I did want to keep this completely de-daconized. Even though I work from them, I just want to kind of give you an idea about a heat pump. But I also just want to kind of give you an idea of what our products would look like. A lot of the other manufacturers are very, very similar anyway. But just sort of going from the very top left and the one below it. These are monoblock units. These units would these would have to sit outside your property. The sort of black interface to the slightly to the right of that is just a controller that sits on the wall. That can be absolutely anywhere. You can have thermostats will then sit within the space if needs be. And with all our systems, you would also need a hot water tank. So just moving down the list ever so slightly, we have LT splits. Effectively, what it means is low temperature refrigerant splits. So instead of the water going outside the building like the monoblock would, these have refrigerant pipes going into the indoor unit, yeah, which is then connected to a hydro box, which effectively with monoblock, that's all inside the outdoor unit, which would then connect to a domestic hot water tank, or we also do one that's combined a hydro box and a hot water tank together, which you can sort of see from the second line on the bottom on the left hand side. And then the units sort of carry on going across to the right, but they're just getting becoming bigger capacity classes. And capacity class will purely be down to the size of your property and the heat demand of that property. Okay. And that's it. I'm done. Thank you very much. And
Oh, thank you, Robert. Thank you so much. And I know that this information we can make available, and I know you've put the website address in there as well, which is fab. But I can see as well that there are quite a few questions that have come in, and we do want to wrap up certainly within 10 minutes. So Sean, can I pass it on to you first?
Yeah, sure. Christopher asks about the noise regulations around air source heat pumps. Apparently they need to be 10 metres away from a neighbour's habitable window. So how does this restriction work with terraced or semi-detached houses currently in the UK? Because that's been an issue with his installation.
I'm not totally up on all the regulations. I don't think I've ever heard of the 10 metres away from a neighbour's window. There has to be within a certain noise level, within a certain distance of a neighbouring property. That is correct. What you would normally do at that point, you would sort of speak to one of the installation teams, and they would be able to sort of say what noise level would comply. So a lot of our smaller units and one of our deluxe units, you can hardly hear it run. It's that quiet on the outdoor unit. The only thing I could say is just try and go to one of our sustainable centres and actually physically listen to them run. They are quiet. Please don't be wrong, there are some manufacturers that are not.
Okay. And Janet asks, what is the refrigerant and what would be the implications if it were to leak? And what happens with that at the end of the life of the kit? So
there's regulations that have to be abided to. Depending on the quantity of the refrigerant within the system, logbooks would need to be kept. Most of the air source heat pumps are actually below that requirement. The type of refrigerant in most of our systems now is R32. If it was to leak, yes, it is damaging to the environment. It is something that Daikin take the utmost in care of, making sure it never ever leaks. The one thing I want to sort of drive home, excuse the pun for this, but a lot of people see that car garages was advertising to charge your car up for a certain amount of money. Knowingly allowing refrigerant to be released, if I remember rightly, it's something like a £10,000 fine and 7-year imprisonment. It physically is that strict for us guys out in the field. The chance of a system leaking on these types of systems, it's incredibly rare, and there's generally something majorly wrong if it is doing that.
Okay. And Peter asks, does Daikin offer air source heat pump plus MVHR full house system, same as the single room Ururu Sahara A2A HP?
Ururu Sahara, yes. We have been doing MVHR for many years. If anybody doesn't know what that means, sorry, it's mechanical ventilation heat recovery systems. We never did a residential unit up until recently, and we're now just about to start selling the Duco products. So we will have MVHRs that can be purchased from us as well. Was there a latter part of that question? Sorry. The Ururu Sahara. Sorry. Yeah, the Ururu Sahara is an air-to-air heat pump. It's really unusual, that unit, to be honest with you, because that is one of it's a small little air conditioning unit that would go in your living room, and that actually does fresh air, humidity control, high filtration, and it can heat and cool, dehumidify the room, everything. It's a very unique unit. Okay. I think Kathy is asking which of these heating systems is made in Britain. I'm assuming that's a question to everyone, including spare parts. So all of our systems, these are all European units, the air to water heat pumps. These are all being built all across Europe. There's not one place in Europe that it's specifically coming from, but it's all across Europe. The compressors will come from the likes of China and Thailand as well. Okay, maybe we can find out about the other products at the end. David asked, who will service and look after an air source heat pump if the installer goes out of business? We can, or we can put you in touch with local service companies as well. It's totally up to you. We offer service packages as well, because we're also, we've been concerned to begin with. It's not so much of a concern these days, but originally, as the technology was taken off within the industry, people were having these concerns, and we just said, well, look, we can give you a fully comprehensive cover if you so wish. Okay. And Sharon asks, how much electricity does a heat pump cost compared to gas central heating? if it's designed correctly, and this is the most crucial thing, is making sure the air source heat pump is designed correctly. If anybody is thinking about having anything like that, then the key thing is making sure you get the heat loss done correctly and the design done correctly, and they'll actually give you a more accurate of what the savings can be. But if you're hitting a COP, a seasonal COP of 3.5, that's slightly cheaper than gas running costs at the moment.
Okay. And then Jude asks, she said that there's problems with heat pumps if there's a power outage.
Yeah, but that's the same for any heating system. Even if you've got a boiler, your pump's not going to run, so you're not going to get any heating. Unfortunately, the only way around that is if you've got a good old fire stove, which I don't want to talk about because there's emissions to that as well, but that's what it is.
And what about installation costs? Are they now coming down? Will they carry on coming down?
Yeah, with all these technologies, Octopus, sorry, I didn't mean to name somebody, but Octopus are driving for much cheaper installations. But it depends what needs to be done to the property. If it's just a matter of replacing your boiler with a heat pump because it can run at a very low flow temperature, obviously the cost of that installation is going to be a lot cheaper. If the whole house needs to be repiped and new radiators everywhere, obviously you can imagine that installation cost is going to go up quite considerably.
And David asks the question, are air source heat pumps suitable for 1860s brick built houses?
Yes. I've got an air source heat pump. I've got a solid brick. It is a 1940s house, but it is just solid brick, 220 mil thick. I have insulated it though, and I think that's the key for anybody. I think all three of us would basically say that the first thing you should always do is insulate a property.
Yeah. And a question I've got is, does it need to be physically located on the walls of the house, or can it be located, say, 10 meters away in the garden? Would that reduce the efficiency?
Yes, that's a good question. It can be mounted as long as there's enough free air to move across the unit. It can be mounted up against the wall, it can be mounted on the wall. It can be mounted, some of the units can be mounted 50 meters away from the property. Obviously, the further we're going to have to move the heat transfer fluid, whether that be the refrigerant or actually just water, obviously the further it goes, the more it's going to cost you to move that volume of water. And there is potentially some heat loss that can happen, but generally the pipes should be very, very well insulated, and that heat loss would be very, very minimal. So we're only talking about maybe £20 extra a year to do so.
Okay. And Sally asks, night storage heaters don't require electricity to output heat, so it's only a problem if you have a power outage for longer than 24 hours. So I guess, is that referring to one of the other questions?
Well, if the night store heater is charged up whilst the power supply is on throughout the night, then you've obviously still got heat within that night store heater for the rest of the day. I will add this though, I actually grew up in a house with night store heaters, and I said I would never ever have again. The heat was so intermittent. You were very, very hot first thing in the morning, and unless you had a boost during the day, by the end of the evening you could end up being quite cold unless you were going to switch it over to normal rate tariff to actually run night store heater. So it is something to be careful of. It's not something to be knocked. They are still an interesting concept, but it is something to be careful of.
And I guess if you had some like Tesla power pack, something like that, where you're storing that electricity, could that be used to run a heat pump for, say, 24 hours? How long would that last?
The power pack's big enough. So I've got 16 kilowatt of batteries, and I could possibly run the heat pump at full pelt, if you like, for about 4 hours, and that's it. It would drain the batteries. Right.
Okay. And David asks, could one be mounted in a large roof void?
No.
Is that too heavy?
No, it's all about getting easy free air across that unit is the most important thing.
Well, that's fantastic. That was a very nice. I thought you were just going to say no, and I could just stop there in terms of the questions. But you're coming back in and giving explanations as well. So that is absolutely fantastic. Also, I'm not going to give anybody a test on all of this. I think you've all been very clear that there's lots of information out there, and certainly something I've taken from it is the way in which exploring the different options for your particular home in your particular way of living within it, and your particular budget is something which is very important to do. and the information is out there, and there are people there to advise and so on. I'd like to say a big thank you to Ian and to Adam and to Robert. And I'm now going to just pause the recording, or rather stop the recording, so that we can all perhaps put on our